This is so important for America that this has to happen, and it has to happen in the right way. And America has actually walked away from opportunities in the past. As many of you know, 3 Mile Island virtually shut down the nuclear industry. That resulted in the building of as many as 40 coal-fired power plants, and as a result of that, America is loading the atmosphere with CO2 faster than any other nation on Earth. That would not have happened had the nuclear industry not been shut down after 3 Mile Island in 1978. The natural gas industry is still in its nations, at least in terms of gas shale. There are a lot of people out there that would like to see this industry shut down as well. And the people who were talking about this, but a lot of this is by innuendo only. In fact, as the famous closing scene in Gasland shows someone lighting a faucet, well, of course that faucet is going to be lit. That person drilled a water well through a coal bed. Coal beds produce methane. One of the ways that you do that is by drilling wells into the coal beds and whatnot. Now the punchline here is that in the case of the Youngstown, Ohio earthquakes, the pumping of water down into the ground in large volumes, and I emphasize large volumes because the volumes pumped into the ground in the case of the Youngstown earthquakes is considerably larger by a couple of orders of magnitude than the amount of water that's pumped into the ground for an initial fracture stimulation of any sort. All right, now the second line here says a fault is a fracture in rocks, fracture is a break. It's what keeps the rock from being continuous and solid. That break is across which the rocks move. Faults come in all sizes, from very small to very large. Now, a very large fault, of course, you know, in the United States is the San Andreas Fault. And earthquakes scale proportionately with size, so that here in the eastern United States, there's no chance of having an earthquake the size of one that might occur on the San Andreas Fault, largely because the faults themselves are not as large, and the size of the earthquake scales with the size of the fault. Well, where the fault was, they can determine how deep it was, and they can determine the orientation of the fault. Did it have a north-south direction or an east-west direction? Now, just because the north-south shear wave, or S wave, is the largest here, that doesn't mean the fault zone is oriented in the north-south direction. There's other information that helps us locate the orientation of the fault zone. All right, now, what about this stress being converted to strain energy? There's a way of measuring energy in the earth, and we can normalize that. Let's normalize it to a typical U.S. home, which uses about 1,000 kilowatt hours a month. And seismologists identify the size of earthquakes. For example, that Youngstown earthquake was on the order of a magnitude 4. So you can read this table, look over to the right-hand column, and see that the energy of that earthquake was equivalent to the energy consumed by 16 American homes over the period of a month. Now you can either say, that's not very much energy, or you can say, holy cow, that's a whole lot of energy, depending on your perspective. Actually, it turns out that 16 U.S. homes is sort of a drop in the bucket in terms of the total energy expenditure that it takes for Americans to live the life that we live. And 16 kilowatt hours is not very much natural gas if you were going to burn it. Not a lot of energy was released during that earthquake. On the other hand, if you look at the size of an earthquake such as the Fukushima earthquake right there, if I read that correctly, the Fukushima earthquake, which is a 9 on this scale, or approximately a 9 on this scale, it would take the energy necessary. The Fukushima earthquake, the release of energy during the Fukushima earthquake was the equivalent of the amount of energy consumed by 500 million earthquake, 500 million, how that was. The context of that was that the Russians, the Soviets, had just finished an earthen reservoir with an earth-filled dam that extended 1,000 feet in the air at the height of the World Trade Center buildings. And the pile of water, or the lake, if you like, that was constructed behind that, put enough weight on the earth that it was causing earthquakes. And those earthquakes were induced earthquakes. And so the team that I was with was looking into those earthquakes. Then I was taken from there to what is now the state of Georgia. Then it was Soviet Georgia, as one of the states of the Soviet Union. I looked at one of the world's largest concrete dams. Now, Hoover Dam is a big dam, but this one in the Caucasus Mountains was much larger yet. The weight of the concrete and the reservoir behind that was also going to cause earthquakes. Now, my career largely has involved understanding earth stress, not understanding induced seismicity. So remember the steps. First step is the earth is stressed. The second step is that there's a lot of faults. The third step is that these faults are released. The faults release earth energy in the form of these seismic waves and heat. And mainly this team that went from the United States to the Soviet Union was studying that third step. I was studying the first, earth stress, at that particular point in time. But that was just about as much fun as the State Department dinner that we had or lunch that we had just last week. You know, there was a period of negotiation in which I sat as a 29-year-old or a 30-year-old, if you can imagine being that young, across the table from a bunch of Soviet scientists who, a number of them had gold teeth and gray hair, and at the time I just generally thought they looked fierce, which was not the case because these were very nice people, but it was a bit intimidating. There was an American flag and a Soviet flag, you know, the red flag with a hammer and sickle in the middle of the table, and that was more than just a little bit intimidating. But the scientists made me feel very comfortable during that particular period of time. So, at any rate, induced seismicity has been around for a long time and has been studied for a long time and was one of the principal focuses of the first scientific exchange after Nixon and Brezhnev sat down with one another and said, we've got to do something that makes more sense than having the Cuban Missile. All right, now human-triggered earthquakes. That's what we're really going to talk about today. These are the triggered earthquakes that are triggered by human activity. But strain is released that has accumulated naturally. So in other words, that weight of water on the big reservoir that occurred, actually this was in Soviet Central Asia, this earth-filled dam of 1,000 feet. In fact, it was in the country that is now the state of Tajikistan. I got to go to a lot of the stands back there in the 1970s in Central Asia when very few Americans actually saw that country. But we're going to talk about triggered earthquakes. The strain is already there, and human activity does something. And in this case, human activity is going to pump a little water down into the ground. Triggered earthquakes are related to hydrocarbon exploration. This is one of the next facts that you need to understand. The vast majority of wells do not trigger or induce detectable earthquakes. Now, what this says is that the number of wells, disposal wells in Ohio, the number of disposal wells in which earthquakes have occurred are few out of 170 or so disposal wells. This, of course, is a good thing, but it makes figuring out which ones will produce seismicity a challenge. All right, so the situation really is that there are a lot of disposal wells. Now, disposal wells, you all understand, is a well in which you pump fluid down. You don't expect an economic return. When you pump fluid down under the ground, you expect that it's going to stay there forever, which it does.